All right, let's get started. Welcome, everyone. This is the first of several sessions on quantum computing. This is a very exciting time to be working in that field. We're kind of at a juncture where we're expecting technological breakthroughs very soon that will allow us to scale up these systems. So the focus today will be on things you can do as a developer already now if you want to get engaged with quantum computing. You will hear about the software that you can already play with today. What's also exciting is we will have two folks here besides me. My name is Martin Röteler. I'm the lead of Q# libraries development. We'll have two folks representing the user. Andrew Firstman is here from a startup company, and they are using already our Q# libraries. And you'll hear about these experiences. We also have what is very exciting. You can get inspired by quantum mechanical thinking and improve classical algorithms, classical optimization problems. So in a sense, you need 0 qubits for that kind of work. And we'll have Helmut later from our team here in Redmond to tell you about those possibilities. And it's very exciting because you can already reach customers and make a tremendous impact on their business today. I just want to give that quick shout out. At Build, there will be, I think, 6 sessions in total that involve quantum, and you can hear about exciting new stuff that we offer. For instance, Jupyter notebooks, Q# notebooks, essentially a 0 install experience. You can get started with Q# without installing any QDKs. There's basic background about quantum computing, several sessions about that. There's sessions about the dev tools, how they integrate into Visual Studio and Visual Studio Code, and more stuff about Python. So there's a lot of stuff to explore this week. So I wanted to start with just a bird's eye view. Why do we even care about quantum computing? Because quantum computers are not like a panacea. They're not a universal tool that will speed up everything. It's in the contrary, those domain-specific applications that are kind of rare, but we care about them because they're computationally very hard. And you find them, for instance, in computational chemistry. They're problems where we would really like to understand nature in a sense, to understand problems about the energy levels of a molecule, problems about catalysts, how to design catalysts that help speed up chemical reactions. And classical computers reach limits there. They either are very inaccurate, maybe the classical method is fast, but it gives you just a very imprecise and inaccurate answer. Or they're precise, but then they don't scale well with the size of the system. And there are problems like that arising, for instance, in chemistry. I know fertilizer doesn't sound like the most appealing of all things, but actually in the design of fertilizer, exactly those type of problems arise. Fertilizer is made from substances which are initially kind of made from harvesting nitrogen from the air, turning it into compound form, such as ammonia, and then further processed. And that first step in the process is done using a process that's kind of known for hundreds of years, about 100 years, but it's very inefficient. We would like to find a better process. We know it's possible to do it in kind of another way. The nature does that in certain plants, but we have to do it at high pressures, high temperatures, and it just wastes a lot of energy. People estimate about 2% of global energy output just goes into that one process of making ammonia. If we would find a better way, that would have a tremendous impact on our humankind. So similar applications we anticipate in, for instance, capturing carbon from the air. There are processes that do it these already now, but they're very inefficient. So if there was a better way, that would have tremendous impact. So quantum computers have that great promise of being a tool that can help us with that. In material science, similarly, there are a lot of applications. And one of the promising areas for quantum computers are also machine learning applications. There we have not really found a killer app yet, but we have some hunches of things that a quantum computer could help us there. For instance, we know a quantum computer is good at computing correlations, at computing Fourier transforms, and they can amplify certain probabilities, so that all these things together might actually help us building better ML. Historically, the first applications really were in areas that are closer to cryptography, so very mathematical problems such as factoring of numbers. So this is a pretty big number. It has 2,000 bits, or roughly 660 decimal places. It's one of the RSA numbers, and the problem of factoring, or the hardness of factoring, is really underlying a lot of the crypto we use these days. Turns out on a quantum computer, you can actually factor numbers relatively easy. I mean, you still have to build a machine that's quite sizable. If you want to factor, for instance, a 2,000-bit number, you need roughly 4,000 quantum bits, qubits. And those qubits have to be really good. They have to be error-corrected. So when you look at the headline numbers you might find in the press, those are not error-corrected qubits. Those are raw qubits. So we'd have to have around 4,000. Having 4,000 would allow us to factor a number instead of 1 billion years, which is the best classical algorithm. We could do it in that time. We could do it under some assumptions of the clock speed. We could do it in a second or so on a quantum computer. And the same thing is true for other authentication methods. You might have heard about elliptic curve cryptography. So our team in Redmond has analyzed those and has found very similar cost estimates in terms of the number of qubits you would need and the number of operations you would need. So you could also break that, and that's the authentication used in a lot of blockchain technologies. So we would have to change that technology to another technology. The good news is there are proposals how to replace cryptography with a quantum safe form. I want to give a big shout out to the group that Brian Lamacchia runs at MSR. So right now there's a standardization effort going on by the US government, by NIST. So they have a call for new crypto systems, and Microsoft has several contenders in that race, and it's a very interesting field, like how crypto shifts towards quantum resilient crypto. So fear not, there will be new kinds of crypto, even when a quantum computer is around. But crypto is not really a good business case, because how many crypto applications will you be able to sell, right? Maybe a few, maybe some government agencies care about it, but it's not a real business case to make a lot of money from it. So to understand that a little bit better, let's track back and think about, like, what can we learn from nature, really? So kids are great with that. Kids ask us questions like, hey, why is grass green, or why are leaves green, or why is the sky blue? And we don't even think about much why. But really the reasons for that are fundamentally quantum mechanical, right? Understanding the sky, for instance, you have to understand scattering of light and so on. So really what we try to do in quantum computing is learn from nature and harvest that and turn it into applications. And the prime example is quantum chemistry. So in a nutshell, what goes on is you have a system like a molecule, and now you try to model that. And chemists have been doing that forever. So the typical way to model it is to ignore most of the structure of a molecule and just focus on the electronic structure. Then you arrive at a certain matrix. Physicists call it Hamiltonian. And we'd like to understand that and like to understand its energy structure. They're so-called eigenvalues, and we'd like to understand them. Typically only the lowest level one, informs us a lot about the properties of that molecule. And a quantum computer is really good at that. And why? Because it's a controlled quantum mechanical system. So if you have another quantum mechanical system, you can map it to your controlled system and study the time evolution of that system, which in turn informs you about the system you care about. But it's not as simple as that. So that has been known for quite some time, that simulating time evolution is something the quantum computer is good at, but there's a catch. Even if you have an efficient way in the sense of polynomial, a kind of a polynomial slowdown, that polynomial can quite likely kill you if the degree of the polynomial is too high. So the first algorithms in that sense had a scaling of, I think, n to the 11, where n is the problem size, typically the number of basis functions. So if you had such an algorithm, you did a molecule that people really care about, such as ferredoxin or nitrogenase. Nitrogenase is one related to the catalyst problem of harvesting nitrogen. Then you would still end up with a runtime of many billions of years. That's polynomial, but it's kind of slow. So people in the team at Microsoft here in Redmond, and several are in the audience, Matthias Treuer, for instance, there were other people, Dave Wecker and several others, worked on chipping away slowly the complexity of that algorithm, and finally brought it down to something that could actually be done in a, say, realistic quantum computer having a realistic clock speed. So the point here in that slide is that in the quantum world, we have similar things going on like in the classical world. We need to have quantum algorithmic thinking, and we need to be aware of the runtime. And just having polynomial is not enough. We need to kind of develop techniques that allow us to reduce the complexity. And of course, ultimately, we want to program these algorithms. We want to kind of be able to, even now, want to be able to write the programs that we can later run when the quantum computer actually scales up to that size. We want to have the programs ready, understand them before, so that we can find kind of bottlenecks. We want to be able to profile them and identify good algorithms. So that's part of that slide. So really, that molecule is one people care about a lot in like a nitrogen fixation. It's part of a really, really big molecule. It's so-called the active site is just visualized here, which is much, much smaller than the entire complex. And our team has costed out in a work that was published a few years ago. And we found that in a few hours on an actual large-scale quantum computer, we could solve that problem. Okay, so at Microsoft, we try to build an entire end-to-end stack for quantum computing. So it starts with the kind of the application layer, software layer, where you express the high-level algorithms. But then it goes all the way down to the quantum device, and it needs to have another layer that is the glue between these two extremes. There's a lot of classical control that needs to happen. So we have this end-to-end stack view where we want to really develop all the components. In this talk, I'm going to focus on the top-level component and want to present you the software. So the software is based on a language called Q#, and like C# and F#, it draws on some multiple paradigms of programming. It has functional flavors to it. It allows you to express many ideas that you might have for quantum algorithms at a very high level. So that's one of the aspirations, is allowing high-level programming where you don't have to worry about bit-level operations so much, right? Nobody really likes to deal with assembler unless you care about for performance, which we can also do, but most of the time you just want to have the idea expressed. And also we care about problems at scale. We don't want to just look at toy problems or like kind of just not realistic problems. We really want to study the problems at scale that would have an impact and move the needle. So that draws us to a certain design in the language, kind of a reusable design, and we target large scale. We can handle any scale. Libraries, they are open source, so we can, people can contribute, people can experience the entire libraries. We try to give some guidance what we're going to do next with libraries, and you can already play with a lot of fundamental libraries. In a moment, you will see one of our main workhorses, the chemistry library. Also, we have dev tools, and they integrate into Visual Studio and Visual Studio Code. There's docs, and we influence the docs team, so because a lot of that stuff is very mathematical, and in math, there's this this language called LaTeX that some of you might have heard. So the doc team now supports MathJax rendering in LaTeX, which is kind of cool. And this whole thing runs on .NET Core. The initial release, the first releases, 01, they were a framework, but then we switched to Core, so we have multi-platform support. This runs on Windows, this runs on Mac, this runs on Linux. And roughly the very high-level picture of how a Q# program looks like is like this. So really there's a driver, which typically is written in C#. It could be written in F# as well. And then that expresses the classical computations that we might do on the side. The quantum mechanical ones are the two kinds. We distinguish between operations and functions. Operations just have side effect on the quantum data and update it. Functions are things you want to do on the side, but they're not meant to be very complicated operations, just small side operations, side computations. And the idea is that those things should map to something you can do with a coprocessor that sits close to the quantum processor. All right, so that those are done by the cryo control, part of that stack. So that's the rough idea, and we can target then. Ultimately, we want to target our hardware. In the meantime, you can target simulators, and we have kind of simulators work reasonably fast, up to 30 qubits or so. Then you really suffer from paying that exponential overhead of simulating a quantum system, which is exponential in the number of qubits. And you can also already now use a profiler. The profiler is completely scalable. It just counts how many qubits are there, how many gates do I have, and other metrics, such as the depth of the circuit delay. Those things you can already do today, and you can do it at scale. You can write really large-scale applications like Shor's algorithm or chemistry, and basically push a button and you get that profiling information out. It's really tremendous, really cool. And you don't have to rewrite your code. You protect your investment. The code you write once and you explore today, you ultimately will be able to run on a quantum device. And the big news of today, some of you might have seen it, so we had already the libraries and the samples were open sourced. We now announced today that we're going to open source the Q# compiler as well. It will take us a few months in the summer. The team will open source that as well. And also the simulators will be open sourced. Libraries, samples, and so-called katas are already open sourced. Katas is a very cool concept. They're self-paced tutorials going from very simple things to medium complexity things, and they allow you to get started with Q# really fast. So it's really a community thing. Share your ideas, collaborate, engage, and drive our further quantum revolution. Okay, and if you want to learn more, please explore our presence on GitHub, on the docs pages, and we have this main quantum page. Now I kind of want to shift gears, and I mentioned that we have a chemistry library. That chemistry library allows us to capture the problems I mentioned earlier, like the nitrogenase, the nitrogen catalyst problem, for instance. You can model that, and for that you need typically a chemistry modeling software. These softwares are kind of complicated. We partnered up with with the government research lab called PNNL, Pacific Northwest National Labs. They are here in Washington State in Ridgeland, and they have a software. There's a kind of a software consortium they're part of called NWChem. That software allows you to do chemistry modeling, really complex software. But we built an interface to that software so we can actually generate quantum programs that we can then execute in our framework. That will eventually allow you to understand and kind of feed back information about the chemistry problem, possibly updating your chemistry models. So that this library that allows you to do that, we're now kind of offering to the world, and people are using it, starting to explore it. And I'm very excited to announce our next speaker, Andrew Fersman from 1QBit. 1QBit is a startup based in Vancouver, Canada. And I hear our speaker took the water plane down from Vancouver to here. What's cool is they're actually evaluating that library, kicking the tires, telling us the things that work well and the things that don't work so well. And as part of that learning experience, we try to make the library better and have a great offering for our customers. So Andrew is the CEO of that company, 1QBit. He has worked in the venture capital space for a long time. He has startups that work in the telecom sector, satellite, the financial sector. And he leads the company, and he's going to say a little bit about the company. Please give him a warm welcome.
Thanks very much.
Thank you. Thanks.
All right. Well, thank you very much for having me. We'll tell you a little bit about 1QBit to give you some context. We're about a 6-year-old company. We're just over 100 people. We've raised enough money that we can actually focus on some of these slightly longer-term technologies, but not so much that we don't care at all about right now. So I think this is kind of a perfect segue for the kind of different development tools that we're going to be talking about today. We started off doing a lot of IP development, and now we're moving more into commercialization. And our real interest is in sitting here between the difficult industrial problems that were alluded to previously and the different hardware development systems and the tools that are available to be able to tackle these problems that are now being developed. And we've really, really liked what Microsoft's been bringing out. It's allowed us to do a lot of that work much sooner than many people had expected. We're interested in talking a little bit about quantum computing, not just because of the fact that we think that it's interesting, but because some people way above our pay grades think it's especially interesting. And we were sort of commanded to care about quantum computing as one of the few developments that will really be changing what's happening over the next few years. And this has actually been a great boost, as you've seen many people starting to talk about this more publicly. But I think that there's still a pretty sizable gap between the word quantum computing and what people are really doing with quantum computers and what they hope to do with these technologies as they come on board. And for me, the easiest way to understand a little bit about what we are trying to do with quantum computing and why we care about it is to look at these sorts of photos. And what I think is especially interesting about this is not just that this kind of looks like a microbrewery, but more the fact that anybody who's working in a laboratory that's anything from a microbrewery up to sort of cutting-edge chemistry work right now probably recognizes this. And they recognize it because this isn't that different from how we do chemistry today. And the reason that that's a bad thing is because almost every other industry that we can think about has really transitioned to something more like this. The way I like to sort of draw an analogy is it's not a very good idea for Boeing to make a bunch of planes and throw them off cliffs in order to see which ones fly. And yet that's kind of the state that we're in with a lot of chemistry right now. And the reason that we're in that state is because our computers are just not particularly well suited for this task. So we happen to be joined in the audience today by Matthias Treuer, and Matthias had this great quote that essentially says, if we want to be able to actually do the work that we do in the labs in chemistry with our computers, it's no problem as long as we have a computer that's roughly the size of our galaxy. But since I don't own that machine just yet, and because we do need to make a profit eventually with this company, we're really interested in trying to understand if there are better ways forward. And there really are better ways forward. There's three major things that I think are of interest. The first is these quantum-inspired optimization devices. We're going to hear a little bit more about them in just a moment. But basically, being able to recast your problem in a form that makes it amenable to quantum processing is already helpful, especially if you then have devices that are designed to compute to solve those sorts of problems directly. The other thing that you really want is a path towards a scalable quantum computer. And finally, you'd love to have a development environment that allows you to take advantage of both of these things. And the nice thing is, with Microsoft, you really have a kind of a one-stop shop for that, because their Project Catapult is really this great quantum-inspired platform that we're going to be able to use in order to develop applications that can run today, solving some of these difficult problems. Then, of course, the holy grail of all of this is the scalable topological quantum processor that Microsoft is working on. And then, specifically, the Q# environment is a great way for us to be able to build applications that we know will eventually run on these scalable processors, but where we can utilize the coding environment and also the simulators in order to prove those things out today. So at 1QBit, we spend a lot of our time thinking about chemistry, some of these near-term applications. And one of the things that we do is we partner up with large chemistry companies in order to be able to work on the problems that we think are going to be the first things that get offloaded from in the lab to in the computer. And so one of the types of problems that everybody's really excited about is the development of new types of catalyst. Basically saying, if you're trying to do something like dry paint, what can you toss into that paint to make the paint dry a little bit faster? And even though that sounds like kind of a canonical, the most boring problem you could possibly imagine, watching paint dry is actually a super high value problem, and it's something that we're going to be able to do really, really early on with these quantum devices to be able to simulate which things might improve that process. So we've actually put together a quick demo. This isn't exactly that problem, but this idea of the symmetric stretch of a hydrogen ring is kind of like a problem that has all the same sorts of features that you would express when you were going to try and solve the problem of experimenting to find new types of catalysts. And ideally, what you want to be able to do is to know if you're going to be making those rings be of different sizes, then you want to be able to understand what's the essentially the lowest energy state and what sorts of characteristics will these different things have. And to calculate that, right now, you're actually able to fire up Q# and to be able to load up some of the chemistry things that we talked about before. Here we have an interface to something called a variational quantum eigensolver. But essentially, it's really, really interesting that all of this has all been put together in packages that exist right now. And that Q# environment is great for being able to speak natively in the language of the quantum processor. But on top of that, you can then access your Q# from a familiar language like Python. So this, for example, is a way for us to be able to call that code right out of our friendly Python environment from one of our Jupyter notebooks. And in the end, you can actually run a little program. So what I like about this page here is if you look at that dark black line down the middle, that's sort of the ground truth of what the real energy state of this system is. And if you look at the blue dotted line and the gray dotted line, this is sort of the estimated ways that we would use to try and use a classical computer to be able to simulate this right now. And unfortunately, they're just not accurate enough to be usable. But without even having a quantum computer available today, by framing the problem in a way that's sort of thinking about this as a quantum chemistry problem for quantum computers, by utilizing the software tools that Microsoft has provided, and by allowing us to use these simulators, we've been able to write software that we can put together, run through exactly the pipeline that I just discussed, and all of our data points that came out are these little red X's here, which really do a great job of summarizing that curve. And so this is exactly the kind of stuff that we can already do today, but what's interesting is that as these machines get larger and as we're able to do bigger and bigger simulations, we're going to be able to scale these up to be more and more interesting simulations that allow us to build completely new things and to have a totally different relationship with the built world because we're able to know the properties of different chemicals that we haven't produced before. And so when I think about what 1Qubit's really working on, that's sort of the gold star. This is the thing that we want to do in the future. And at the same time, we're able to do a lot of work today by partnering up with Azure. For example, we're about to release a quantum-inspired platform for being able to address a whole bunch of the problems that we're going to hear about next. But the way I like to think about it is, if you're looking to be able to understand what we're going to be doing with quantum computers in the near future, or if you're interested in being able to harness all of the thinking that's going into building those devices to solve really difficult problems today, you can do all of that through Microsoft and through Microsoft Azure. And to hear a little bit more about those quantum-inspired things that are happening at Microsoft today, I'm pleased to welcome to stage my friend and colleague, Dr. Helmut Katzgraber. He's a principal scientist at Microsoft, and he's going to take the long way around here to come up and entertain you for the rest of the program.
Thank you, Andrew.
Thanks a lot.
Thank you all for still staying here in this late time of the day. So what I'd like to do is shift gears a little bit and talk about what we like to call quantum-inspired optimization. And as you see, it is optimization with a quantum twist to it. Now, before I tell you a little bit more about quantum-inspired optimization, I'd like to just say a couple of things about quantum hardware and to pull some misconceptions out of this room. There are so-called digital and also analog quantum computing devices, and they're very different in their nature. Digital devices tend to nowadays typically have a smaller qubit count. They're programmable, for example, via Q#. In some sense, the same way that you would program a regular computer. You have a programming language, you can implement a problem, you can solve it on the device. They're either made out of ions, superconducting flex qubits, or, like in Microsoft's case, topologically protected qubits. In contrast, you have analog quantum annealing machines. These are special purpose devices. Think of them as a machine designed to do one particular task, in this case, optimization. They are analog, meaning that you kind of get to look at the problem. There's always errors attached to this. And they're made out of superconducting flex qubits. Now, what I want to talk about today is basically a third paradigm that is not quite quantum, but uses some of the advantages of quantum on current hardware. And this is what we like to call quantum-inspired, that we run on standard CMOS hardware or accelerated on FPGAs. And the idea here, again, is to emulate quantum processes on current hardware to solve current industry challenges more efficiently. Now, the focus of this talk will be on optimization, and in particular, quantum optimization. Why? I guess the answer is simple. Optimization plays a very crucial role in everybody's life. If you want to ship something across the world, if you want to do a scheduling problem, if you want to design a drug, or if you want to send a rocket into space, you have to solve very hard optimization problems. Therefore, there is a lot of value to this, and of course, a lot of challenges. Now, quantum optimization has mainly focused on binary problems. These are problems where the variables can take values 0 or 1 or plus minus 1. And the reason is very simple. They have a huge industrial value. I will show you a broad selection of these problems in the next few slides. They have a simple mathematical formulation. Unfortunately, they're computationally very, very hard, but because of this simple mathematical formulation, and Don't worry, I will not show you any equations. They're very well suited for quantum optimizers. Now, I'm going to try to give you a bit of a flavor of how these quantum optimization procedures work, basically by going back a few thousand years to the Neolithic era. Back then, people would take a chunk of metal, heat it up, and cool it down slowly to remove imperfections. This process is known as annealing. Now, back in the early 80s, Scott Kirkpatrick and collaborators at that time at Intel came up with a clever idea. Why don't we emulate this process on a computer? And they called this procedure simulated annealing. They were looking at basically doing chip layouts for their microprocessors at the time. And so the idea is very simple. You basically start with a configuration to your optimization problem. That can be anything, okay? The imagination is your limit. And you attach a temperature. Think of it really as a temperature in the sense of what boils water. So you start off at a very high temperature where your variables or your system evolves. Think again, the water is boiling. And then you reduce the temperature according to a schedule until you reach some target value. And if you do this slow enough, you might find the optimum or the solution to the problem, okay? In the case of water, again, if you cool it slow enough, you might get a wonderfully perfect ice cube without any imperfections in it. Now, quantum annealing is just a quantum counterpart to simulate annealing. All you have to do is replace the quantum fluctuations, replace the thermal fluctuations by quantum fluctuations. So if I now press click on this, you will see this algorithm is going to change ever so slightly. What was temperature before is now transverse field. And basically, instead of doing Monte Carlo updates, which is how you would run simulated annealing on a regular computer, you do quantum Monte Carlo updates. If you want to do this in hardware, what you do is you use so-called superconducting flux qubits. Those are little superconducting metal rings. As you know, if you have a current, who does remember how Lenz's law work? Wow, nobody to physics here? Okay, a couple of hands. So according to Lenz's law, when you have a ring and you have a current going counterclockwise, you have a flux pointing upwards going through the ring. If it goes counterclockwise, you have the flux pointing down. And these are your states 0 and 1. Of course, you can have superpositions of 0 and 1, and this gives you your flux qubits. Okay? Now what you then do is you string these superconducting loops together via some kind of interaction matrix. And this is what you then use to encode your problem. You start with your binary mathematical variables. You represent them on this hardware. You apply a strong transverse field. This induces quantum fluctuations. You reduce these fluctuations slowly. If there is some kind of bump or barrier in your cost function landscape, the quantum system might be able to tunnel through that barrier, and you might find the optimum more efficiently than with a thermally assisted algorithm. Good. Now this sounds great. You're using quantum mechanics to solve a problem. What is the reality for current quantum annealing machines? Well, the reality is a little bit bleak in that there's a few challenges to overcome. The first one is what we call the embedding overhead. Suppose you want to study a problem, think of it as a vertex cover problem, as a matching problem, whatever, something that lives on this topology here, what you see on the left-hand side. Now you see, this is your actual problem with your logical variables that you want to treat. But because, as you saw before, we have a hardwired chip topology that lives on this square grid, we need to take this logical variable 1 and replicate it 4 times, such that you can fulfill all the interactions that variable 1 has with these neighbors. And so you need to strongly couple these physical variables here to create one logical variable on the left-hand side. And you see right away, in this simple example, you have about a 50% overhead in the number of variables that you need to solve the problem. This can get very, very expensive. As I said before, you have analog precision, typically 5 or 6 bits precision. As you all know, that's not very much for a computer. You're locked in with an algorithmic engine that is standard quantum annealing, strong transverse field, reduced to target value. You are able to handle complex cost functions. For those of you that come from OR, things of mixed integer problems, forget about it. It gets really, really nasty. And then finally, to date, I'm very comfortable in saying this, there is no real-world application, something that really matters in industry, where the algorithms that I work on have not outperformed quantum annealing machines. And this is why we're so interested in these quantum-inspired techniques. Having these claims of speed up is what really has fueled my interest in this problem and created a fruitful competition that has made us develop new methods that can solve these problems that were considered to be very, very hard much more efficiently than before. More importantly, if you run this on a regular CPU, we have absolutely no intrinsic limitations, which is great news. And then finally, if you've tried quantum annealing on a problem, we can do it faster, we can do it cheaper, and we can do it better if we just emulate the quantum processes on classical hardware. Now, I've been using this word quantum-inspired optimization a lot, but I've yet to kind of tell you what this actually means. It turns out it's very loosely defined. If you look in the dictionary, inspired means to exert an influence on something, okay? And here, when I say very loosely defined, you have the whole range in the spectrum. On one side, you're trying to really emulate a quantum process, for example, via quantum Monte Carlo or quantum annealing on the computer. So for example, if you have this rough cost function landscape that you see here, and you want to solve it with simulated annealing, then you have to have a very large activation energy to overcome this barrier. And such a move will be very unlikely in your simulation. If you were to do this with pure quantum Monte Carlo, then you might potentially tunnel through this barrier and find the optimum faster. And in quantum-inspired optimization, we're trying to take the best we can out of quantum and implement it in classical hardware. And so I tried to depict this by basically having an improvement over classical, maybe not the full benefit of quantum. This is one extreme. The other extreme is the one that I'm most interested in, which is use algorithms that are commonplace in physics and that we physicists have used over decades to solve really hard problems in industry. And to show you how well these work, let me show you a case study, something that we did back in 2016. Some of you might have heard of a SAT competition or the MaxSAT competition. Basically, SAT is a problem. It's a Boolean satisfiability problem with huge industrial value. A lot of the problems in optimization get mapped onto SAT formulas. In fact, if you want to prove if some problem is P or NP, then you end up mapping it onto a 3-SAT formula. And if it maps, then yes, it's very hard to solve. So in MaxSAT, the goal is to determine the maximum number of clauses that equate to true in such a Boolean formula. Here you have 4 variables, x1, x2, x3, x4. They can be negated, which I denote here with an overbar. And they're connected via logical ORs. And then these clauses of 3 each are connected by logical ANDs. And so the question now is, can you find an assignment to these variables such that you can maximize the number of clauses that are true? When you have just 4 variables and 2 clauses, it's pretty easy. Sit down with paper and pencil. But when you have about 100 of those, you're going to be doing math for the rest of the age of the universe. Now, there is a competition that happens every year by the SAT Association where people have been sending their algorithms over decades. And we thought one year, somebody hold my beer. Why don't we send our physics algorithm to the competition? Well, we did, and we ended up winning on our first submission. This thing here we call Borealis is nothing else than a physics algorithm run on an industrial problem. Not only that, but there was a second team, also folks that are now at Microsoft, Stephen Jordan and Brad Lackey, that submitted their solver based on diffusion Monte Carlo, which is actually a quantum algorithm, and they landed 5th place. Sorry, they didn't make it to my graph. Life is tough sometimes. Now, when should you use quantum-inspired optimization or QIO? Well, there are certain use cases. Suppose you have a given optimization problem in front of you. One of them is, if you want to have a fixed solution quality, you want to find the solution faster. Okay? This is a typical problem when you say, I want to make sure I have at least so much quality in my solution, but I want you to tell me this sooner. For example, if you say, I'm happy enough if it's 90% of the problem solved, but I only give you 1 second to do this. For a fixed solution time, find a better solution. This is very important in things like unit commitment problems. When you're trying to optimize a power grid, they pre-compute the potential load every so many hours. And so, of course, if you have a fixed amount of time, you want to find the best solution possible. And then finally, you want to be able to solve more complex versions of the problem with fixed effort. In the sense that, what if there's constraints? If I'm looking at a routing problem and now I want to factor in that There's more trucks parked over here than over there. What are the characteristics that an optimization problem should have for quantum-inspired? Well, obviously, if it looks like the one up there, it's not good news because any gradient descent will find you the optimum right away. So you want something gnarly like this energy landscape down here, something with a lot of bumps where any kind of local search algorithm will get stuck right away. Okay? You also want a large number of variables because if you have something with 20 variables, you can exact enumerate all possible solutions. Defeats the purpose. And then finally, you want the cost function to be evaluated quickly. Why? Because the evaluation of the cost function lies at the core of the algorithm. Now, I want to emphasize that these methods are heuristics. In other words, you don't get a guaranteed solution. Having said that, often a 1% improvement can be huge if you scale it up to industrial scales. And there's a huge collection of problems that can benefit from these quantum-inspired methods. Starting from circuit fault diagnosis to electronic design automation or verification and validation, which are very important if you want to, for example, build electronic components or build a jet that flies, to chemical, oil, and gas, material discovery, I'll show you some results about that later, unit commitment, as I said, power grids, signal processing, machine learning to a lesser extent because the landscapes in these problems tend to be a little bit more convex, so they're a bit easier. Job shop scheduling and toolpath optimization. If you have a plant that is trying to build a vehicle, how you distribute the machines onto the different teams for different workers to make this happen faster. And finally, of course, traffic, car sharing, and logistics. But as I will show you later, we also have far more exotic applications, such as optimizing MRI's pull sequences. Now, if you want to compare quantum versus quantum-inspired optimization, then first we got to set the playing field, and we got to define what do we mean by a disruptive technology. Well, it should be faster than any algorithm that we have out there right now, or it should have better performance on some specific tasks. So what is faster? Again, here, there's two cases of faster. Let's assume that you're looking at a problem that has a specific number of variables, and you keep increasing the number of variables, and you look at the time it takes you to solve the problem. Typically, these things scale exponential. They're bad news for any kind of algorithm, okay? So a log-log plot will give you roughly a straight line. So faster, which is the ideal case, can mean that you get a better scaling. In other words, the slope of this curve is slightly more flat. But faster can also mean a huge constant offset. If this is 1 billion, then it's definitely worth it, even though the same scaling exists. What is better performance? Well, for example, does it give you a more varied pool of solutions? This would help you in adding additional constraints. And the most important thing that I want you to take away here is that when you see any claims of speed up in the news, you have to be very careful because it strongly depends on the benchmark you use. A simple example is the following. You want to race a Formula 1 vehicle against a rally car. Formula 1 vehicle is clearly faster. But if you're driving on dirt, it's pretty clear which one's going to win, okay? Always balance these things out. Let me show you an example. In 2016, Google published some interesting results using the D-Wave quantum annealer. What you see here is the time to solve these problems as a function of the number of variables using the D-Wave machine labeled here with QA, simulating the D-Wave machine on classical machines labeled with quantum Monte Carlo, against simulated annealing, the thermal counterpart that I showed you before. And when you look at these data, you can see right away that the quantum approach is scale better, the slope is flatter, and not only that, but there's a huge offset of 8 orders of magnitude here. And when you look at this, it sounds really impressive for quantum optimization. And so again, we said, somebody please hold my beer. Let's see what our algorithms can do. I don't want you to try to figure out what is what. Just look at the spaghetti on this screen. Again, here you have quantum Monte Carlo, simulated annealing, and the D-Wave device, and a bunch of other algorithms. More importantly, the purple line down here that scales really well and is comparable in speed is Borealis, the algorithm that won the MaxSat competition. And so what I'm going to do now is, to make this more palatable for you, is compute the slopes for the largest system sizes, in other words, perform an asymptotic scaling analysis, and just show you the slopes for different algorithms. Of course, smaller means better, and as you can see right away, the quantum approaches here are very good, but they're no match against our algorithms. Notice also that I kind of colored in this figure. On the left-hand side, you have what we call sequential algorithms. These are simulated annealing, population annealing, quantum Monte Carlo, the D-Wave device. These are algorithms where you have a control parameter, say a strong temperature, strong transverse field, high temperature, and you sequentially reduce it to a target value. It's a very specific type of algorithm. Then you have the tailored algorithms. That's cheating. I know ahead of time what is the problem I'm supposed to solve, so I exploit some symmetry of the problem. But then you have generic ones like replica Monte Carlo and Borealis, which is based on tempering Monte Carlo, that clearly are competitive and outperform quantum optimization. So we thought we would capitalize on this here at Microsoft and decided to look into this more closely. What is our approach? First and foremost, develop, combine, and improve algorithms. This is very important. I'll get back to this again. We want to build a flexible stack with modular algorithmic engine that is massively parallel. You see, not every algorithm is meant for every problem, so you want to be able to swap that in and out depending on what you're looking at. The advantages are that the biggest speedups to date come from better algorithms. You see, if you want to double the speed, you have to double the size of the machine. If you come up with a better algorithm that scales better, you don't have to double the machine. Our devices are digital, meaning that we have a larger application domain, and because we can do an all-to-all connectivity with k-local interactions, we'll explain this later, and have digital precision, we have no need for mapping or embedding. And so we develop our codes on CPUs, we run them now on FPGAs for speed, and hopefully one day we will run them on quantum-accelerated hardware. Let me show you how well this method works for real-world problems. In 2017, Neukart et al. Published this following study where a quantum annealer was used to optimize the traffic of 480 vehicles in Beijing heading to the airport. The heat map here represents the traffic. Now, if you solve this with traditional methods, it takes you about 800 seconds to solve the problem. If you solve it on the quantum annealer, you're looking at 20 seconds. If you use our approach, it's 0.02 seconds. And if you accelerate on the FPGA, it's 0.0004 seconds. Now, at this point, I'd like to just shift gears a little and show you now how we can capitalize on this to solve real-world problems today. And here I want to highlight 4 of the core strengths that we have. One is algorithmic expertise, large-scale scalable hardware, modular software, and more importantly, domain expertise. Having people that can think about the problems and cast them in a form that makes them easier to solve is as important as having good hardware, if not more. The first one I want to talk about that highlights our algorithmic expertise is optimizing Seattle's traffic. I think everybody had an issue, unless you happen to be staying at the Sheraton, getting to this building today. Seattle is horrible, especially if you cross a bridge. Avoid it at all times. So the objective was to optimize rush hour traffic using our quantum-inspired optimization techniques. What's the current status? If we take Bing's best recommendations and look at real-time traffic data, we can find 50% or less congestion, and we can reduce travel times by about 8%. Now, remember the case study I showed you before was on 480 vehicles, so we thought, let's kick it up a notch. And for this, we had Frances Tibble and Anita Ramanan, sitting here in the second row, being kind of shy and not doing this, do a phenomenal job in implementing this with the help of Brad Lackey, and they just ran this for 5,000 vehicles. Well, here you have a live demo on this. You basically select the number of vehicles. We look at the 5,000 vehicles out of 5,000 random locations in Seattle. We keep each vehicle 10 different options to travel. And now you see this is nasty traffic, but you see at the bottom how the congestion score keeps going down. And after 2,000 steps of our optimizer, if you compare the results, I don't think I need to convince you that things look much better on the right-hand side than on the left-hand side. Again, not my job. These two did the brunt of the work. They're awesome. Good. Now, the next example I want to show you is actually work together with our partner, 1Qubit. And here I want to show you how we can tackle hard optimization problems in chemistry. What we did here on the software side is use Microsoft Quantum Inspire Toolbox. And on the hardware, this is what I want to highlight here, we have a configurable FPGA cloud at a massive scale. This is what we call Catapult version 2. What is it? Basically, a lot of the server blades in Azure have built-in FPGAs. Now, this by itself is no news. What is amazing about it is, as you can see, the FPGA is connected with a 40 gigabyte per second line directly to it. Not only that, but you have a fabric that connects the FPGAs natively card to card, which means that we can run problems at a massive parallel scale on FPGAs and solve things that most people would say today, there's no way of solving them. So to just show you what we can potentially do, I'd just like to show you an example from work that was done by Maritza Hernandez and colleagues at 1Qubit, which is graph-based molecular similarity. It's a very important problem in chemistry. As I said, this is key if you want to make sure you don't wait too long for paint to wait. What you have is you have a bunch of molecules, and you want to know by how much do these molecules agree. And so what you do is you map the molecules to a graph. Then you create what is known as the conflict graph. And this is the hairball that you see on the left. As you can see, it's very conflictive in its nature. You solve the so-called co-K-plex problem, which you see here by coloring in certain of these dots. And we can do this about 500 times faster on the FPGA without the parallelization. And then you go back and you decorate your graphs, and then you do scoring and map it back on the molecules, and you can see which molecules agree and disagree. Why is this important? It's not just important if you want to see paint dry faster, but think about it. If you compare the molecules for heroin and codeine, they're very, very similar. You would like to have a codeine that is stronger but doesn't have the side effects. And the only way to find these molecules is by comparing them. Again, access to larger molecules. The next case study where I want to highlight our modular software is with a partner called OTI Lumionics. On the right-hand side, you're watching a video of one of OTI's transparent organic LED screens that you can use for head-up displays. This is really cool. They're specialized in making these screens and create new organic molecules for display technology. So their approach combines machine learning, a simulation/Ising solver, which is the optimization step that I'm after, with property testing and material synthesis and validation. If they don't find the material with the desired properties, they just iterate, add what they found to their database, and keep going until they have what they want. And I want to focus here on the Ising solver. Their Ising solver can handle materials with about 250 molecules, and they have demoed material discovery on a quantum annealer. So we said, well, let's have a look at this. Now, what is the difference of what we do to what is typically done in quantum optimization? In quantum optimization, you're locked in to handle what we call two local Hamiltonians. These are problems where each variable, the blue dot here, can only interact with one or the other neighbors. Okay? Think of it as a party where everybody's only allowed to hold hands with one person, but there's no kumbaya where everybody holds at some point. The native problem, however, on the left-hand side, as you can see, can have higher order terms. 3 people holding hands, 4 people holding hands, and so on and so forth. And so what we can do is, instead of having to look at the two local problem, we can just look at the k-local problem. Now, for the sake of time, let me show you what happens. If you look at the k-local problem with 48 variables, this turns into a two-local problem with 3,000 variables. And if you look at the one with 95, you get something with over 10,000 variables. Needless to say, solving something with 10,000 variables is really, really hard. And as a matter of fact, what we can solve in 9 seconds would otherwise take more than 24 hours. And this thing here that we solved in roughly under 4 minutes, nobody has been able to solve before. Okay? So we can solve currently intractable problems just by looking at them in their native form. Now, the final thing I want to show you, which I think is very exciting, is work with Case Western Reserve University, where we're trying to advance MRI research. And the objective is simple: optimize MRI scans. Okay, make them shorter, make them better. The idea here is very simple. In an MRI, you have electromagnetic pulses that excite the hydrogen molecules in your body, and then you have coils that pick up that signal and determine, is it fat, is it bone, is it muscle, and so on. And so you have a specific pulse sequence that will tickle these atoms in a specific way to be able to discern, yes, tickle, to discern the different types of tissues, okay? Here, the idea is not to change the software, not to change the hardware, just program the machine differently and see if we can do better. So it's an iterative approach. We optimize the pulse sequences with diffusion Monte Carlo. Then we do in vivo scans. We put somebody in the tube. We hope that this person doesn't get fried. It hasn't happened yet. And then what we get back, we feed in, and we just keep going like this. Let me show you some results. What you see here is 2 scans. On the left-hand side, we have our QIO-inspired scan. On the right-hand side, you have the prior state-of-the-art. If anyone here can tell me that they're different, I won't believe it, because they're very much comparable. However, the stuff on the left is a pulse sequence that is nothing anybody has been able to envision before. And that's huge, because it can unlock shorter scan times, better quality imaging, you name it. Now, you might say, well, why are we doing this? Why are we emulating quantum processes on classical hardware? Well, why? Number one, because we want to deliver quantum solutions today. But number two, because we can just cross out inspired. Ooh, something happened with PowerPoint here. So what if we have quantum hardware? The algorithms that we use in physics have typically a random walk at the core. If we replace the classical random walk by a Szegedi quantum walk and implement this on quantum hardware, we get automatic quadratic speedup over classical hardware. In other words, any algorithms that we develop today, we can run tomorrow quadratically faster on quantum hardware. With this, I'd like to thank you. As I said, always think algorithms first. Download Q#, invent new quantum algorithms. That's where the big improvements will be. Engage in the QDK, engage in our quantum network, learn more about quantum, and if you have questions, shoot me a message. Thank you.